inverse functions and logarithms. And first of all, there's one-to-one functions. So the thing, well, let me try to explain a little bit about how inverse functions work. So I kind of think one way that you can think of a function is as like a box like this, where you put in a value and then, whoa, another value comes out. Okay. Now, an inverse function would mean that the inverse function would be like you restore. Okay, so if you take that value that came out and you put it into the inverse function thing, then you're going to get, yeah, you get back the original. Okay, so a lot of times you can't, this can't be done. Okay, so like for example, let's say that X is a bunch of ingredients to bake a cake. And so you like mix it all together and then put it in the oven or whatever, and then boom, you have a cake, right? So here you have like, you went from having these ingredients here to having a cake. Okay, so but it'd be kind of hard to take this the cake, and put it back and get the ingredients back. That'd be pretty hard. You could say there's no inverse function for that with the current technology. Okay, so there you go. So that's, and so sometimes functions don't have inverses, but in math, the reason that doesn't have inverse is because it's a little more subtle than that, and that's because, like, let's say for example, we take this function here, x squared, and we know that f of 2 is 4, right? But if you have a 4 right here, you don't know whether it came from a -2 or a 2, because f of -2 is also 4. So 2 and -2 gives you a 4. So if you only have the 4, then you don't know which one it came from. Okay, so you can't. So this is so we can look at it this way. 2 goes to 4, and -2 also goes to 4. But if you have a 4 here, then you don't know whether that came from a 2 or a -2. Okay, so that kind of function would not have an inverse, and that function is not one-to-one. A function f is called one-to-one if it never takes on the same value twice. Okay, so here, this function here took on this same value of 4 twice. Once when we put in the 2, and another time when we put -2 in. So that's not one-to-one. Okay, so the exercise number 1 is, what is one-to-one the function? And it never takes the same value twice, is this one here. And how you can tell?
The definition of a function is that it only has like each input will only give you one answer, right?
Yep, that's the definition of a function. And
so is that
to
because
be a function, to be a function, you have to satisfy the vertical line test.
Mm-hmm. So is that okay, so that way it'll work with inverse functions?
The inverse function is different. Is inverse function. So this right here is a function, mm-hmm. But it's not a. Wait, what do you?
No, I mean, do they set the definition of a function as a only one input will give you, or for the input you can only get one output? Is it so that way inverse functions can work? So that way that you know what the output was that you gave you like if you try to go in reverse that it would work, because it could only be one.
Yeah, well, yeah, of course. If it's but oh yeah. You can think of it that way. I see what you mean now. Okay. So but the word would be relation. If you don't know it, like you'd have a relation that goes both ways, but then
I see.
Or something like that. Okay, so to be a function, you have to pass the vertical line test. To be one-to-one, you have to pass the horizontal line test. Because here, this, for example, in this case right here, we have -2 and 2, which both gave us the same values, 4. And so, but you can draw horizontal line that goes through those 2 points. So it's a horizontal line test for determining whether a function is one-to-one. One other thing, let me see if that's on the next page. One other thing is, before we go to the next topic, is notation. And the inverse function is defined like this, okay? F to the -1. Now this is confusing because it's not 1 over f of x. It's not that. Okay, no, it's not that. And so that's a little bit confusing. Well, this just means, and because usually, like, if you have like a to the -1, well, that's 1 over a, right? So this is a little bit confusing, admittedly, the notation, but this is referring to the inverse of the function. Okay, so yeah. So but let's go on to some more examples. Number 2. Remember, a function can be determined with a table, and this function here is not one-to-one because it has these two values are taken on with different numbers in the domain. And this one doesn't satisfy the horizontal line test. Okay, so that's not a function either. Okay, let's move on here. They're not they're not one-to-one. They're not one-to-one. They're functions, but they're not one-to-one. Okay, so number 4 is the function f of g of x equals 7 minus sine x 1-to-1. Well, sine x looks like this. Looks something like that. And then negative sine x is going to look like this. And then what this one is basically is negative sine x plus 7. So that's just going to be shifted up by 7. Okay. So that's just going to be the same thing, but just shifted up by 7. Okay, so that's going to be, so the answer to that one is no, because the horizontal line test fails. Okay. Okay, so the inverse function, if f is 1-to-1, then its inverse function, f inverse, is defined by this. F inverse of y equals x, if and only if f of x equals y. Okay, so these are the two keys to how that works. So if you start with the value x, you apply f to it, that gives you f of x. If you apply the inverse to that, you get the original back. Likewise, if you go in the reverse order and we apply f inverse first and then f, you get the x back. Okay, so this is f of x does something to x, f inverse restores the original value back. Okay, so let's take a look at number 5. Here, they just want you to find the inverse of 8. Now, you don't have to go and find the overall. So this would be really hard to calculate the inverse function of this. That'd be pretty hard. But if you notice, if you plug in a 0, what do you get? To key in here, what do you get? You get 8, because e to the 0 is 1. So 7 plus 1, that's 8. So because 0 gave you 8, then the inverse applied to 8 has to give you back to 0. Okay, so 0 is the answer there in number 5.
But is that just a guess that you like threw out there? Just like, let me try 0 and it happened to work?
Yeah, yes, exactly. But because 0 is pretty easy to plug in. So I mean, you look at the function here and you start plugging in a few points. What's the easiest?
Yeah,
the very easiest point to plug in is 0. So yeah, it is a kind of a guess on that. It's a total guess there. But not without any hints as to what you could do. I mean, if you try to take the inverse, try to find the inverse function here, that's pretty difficult. So then that's the only way you have to start guessing. Okay, so let's take a look at this one right here. This is a one-to-one function. Notice that it satisfies the horizontal line test. So part A is it passes the horizontal line test. So it is one-to-one. Okay, now the thing about domain and range is the domain of a function will be the range of the inverse. And the range of a function will be the domain of the inverse. Okay, so it's asking what the domain of f inverse is. This is going to be the range of f. Okay, so and it goes from -1 to 3, from -1 to 3. And the range, that will be the domain of f. And that's going to go from -4 to 2. Okay, next one, what's the value of f inverse of 1? Well, what you have to do is you go over to, you come over to this one here. And you come back, and that's going to be the value right there. So it's going to be -1. And then the next one, what's the inverse, f inverse of 0 to the nearest tenth? Okay, so what happens is you come over here to 0 right here, which happens right there. And that looks like about -2. So that should work. Let me try to make this clear. So you start here at 1, and you come over, and what's this? What's the x value that gives that to you? Okay, so that's a little bit. This is just the opposite of, or kind of backwards when you're looking at just trying to find function values, because we're trying to find inverse function values. Okay, any questions about any of that? Okay, so there is, the reason that we went into inverse functions here is because we want to talk a little bit about logarithmic functions, which are very important for calculus. And it's like this. So you have an exponential function, and the base is b. The inverse of that exponential function will be the logarithmic function with base b. Okay, so this, for each value of b that's positive number, you have a different logarithm for each value of b. So the whole function is different for each value of b. And then the x values the x represents putting in a number from the domain, okay, which would be a number from the range of the exponential function. And then the natural exponent function, which is like that 2.7 something, e to the x, its inverse is the natural logarithm, which is ln of x. Okay, so here we have y equals e to the 7 minus x, and we want to find the inverse function. Okay, so let me show you how you do that. You probably have, I'm sure you have experience finding inverse functions, but here's how the book says to do it. The first thing that you're supposed to do is solve for x. So that's the first thing they want you to do. So take this equation here. Now, if you have an f of x right here, so sometimes it's not y equals that, but it's rather f of x equals that, and you're trying to find f inverse. Then you change that f to a y. And then the next step would be solve for y. Okay, so in this case, what we're going to do is, because the natural logarithm is the inverse function of the e function, I'm going to apply that to both sides of this equation. Okay, and because the logarithm, the natural log is the inverse of this, that means that if I have natural log of e to the x, that's just going to be x. Okay, and so that means that all of this just becomes 7 minus x. Okay, so ln of e to the x is x. ln of e to the x, 7 minus x is 7 minus x. Because the ln and the exponential, the natural exponential are inverses of each other. So they just canceled out, so to speak. Okay, now, so I'm trying to solve for x. I'm going to pull this x over here to that side. Okay, add x to both sides and subtract log y from both sides. And then at some point, you're going to interchange x and y. So change all the x's to y's and all the y's to x's. Okay, so that changed to that, that changed to that. Okay, and this is the answer right here. Okay, so if the original one were like this notation, then the inverse would be 7 minus log x, according to what we just did here. Any questions about that? Okay, let's move on to number 8. Okay, what we're supposed to do is sketch the graph. Okay, now, how do I put this? So if you have f of a equals b, then that, so if you have a point a comma b on the graph, a comma b, if that point's on your graph, that means that on this graph, because this is the graph of y equals f of x, right? If a point AB is on the graph, it's because f of a equals b. Okay, but that means that if we would apply f inverse to b, you're going to get a back. So that means that b comma a is going to be on the graph of f inverse. Okay, so if AB is on the graph of f, then BA is on the graph of f inverse. Okay, so let's come over here and look and see what that means. So here we have the point 1, -1. Okay, that means that the point -1, 1, which is over here, okay, is on the graph of the f inverse function. Okay, here we have the point, the x coordinate is 3, y coordinate is 4, right? So here we have the point 3, 4. That means that the point 4, 3, which is over here, 4 and up 3, is on the graph of the f inverse. Okay, this is the point 2, 2. It's going to be on the graph of both. And if it turns out that if you look at this line y equals x right here, then the way that this concept plays out is you just reflect your graph of f over that line, and that will give you the graph of f inverse. Okay, so all this gets reflected over to that green one. All this gets reflected over to here. Okay, this one gets reflected to there, and then all that gets reflected over there. So the answer is going to look like this one right here. This one here, which is going to be, which one is that? It looks like the last one. Looks like the last one. Okay, and that's just like swapping the coordinates. Okay. Okay, any questions about that? Okay, let's move on to number 9. This is kind of going back. It's defined. How's the logarithm function defined? And it's defined as the inverse of the exponential function with base b. That is log base b of x equals y, if and only if x equals this is b to the y. Because one thing you could do is take b and raise it to both sides. And because of the inverse nature property of the inverse property, log to the b to the log base b of x is just x. Okay, the domain. Okay, so the domain. Okay, so let me back up a little bit. Recall if you have the exponential function, the domain is from negative infinity to infinity, and the range is from 0 to infinity. Okay, because this one, it's either going to look like this, or it's going to look like this. Okay, and in either case, the domain is negative infinity to infinity. The range is 0 to infinity. Okay, so that means, because the logarithm is the inverse, that means that these swap. So the domain is going to be the range of y equals b to the x, which is 0 to infinity. And the range will be the domain, which is negative infinity to infinity. If b is greater than 0, okay, what will happen is it's this situation right here. This is where b is greater than 0. And so what happens is you want to reflect it over this line right here, and it's going to reflect to being something like this. Okay, and so over here, remember I talked a little bit about, for this one, you want to plot the points 0, it always gives you 1, and then 1 always gives you b. Well, over here, in this one, 1 is going to give you 0. And that's the point right there. Okay, so that's 1, 0. And then b is going to give you 1. So that would be, so b is over here, and here is 1. Okay, so it's just like, reversing the order of that second point gives you b1, inversing the order of that one gives you 1b. And the rest fills in. And so here, the y-axis, I'm sorry, the x-axis is a horizontal asymptote for the exponential function. Here, the y-axis is a vertical asymptote for the logarithmic function. Okay. Any questions at this point? By the way, I will make a small note here, and that is if b is less than 1, is between 0 and 1, then your logarithmic function is going to look like this instead. Okay, because your b is going to be here, and that's going to be 1, right? And then this is going to be 1, 0 right there. Okay, and plus, that's what happens when you reflect this over the line y equals x as well. Okay, let's go on to number 10. But first of all, there's a bunch of properties of logarithms that we need to go over. And these are inverse properties. This is just the inverse function properties. And this just basically comes from what I said earlier, f inverse of f of x equals x, and f of f inverse of x equals x. Okay, so that's why, f inverse of f of x equals x. F of f inverse of x equals x. Okay, so those are just the inverse properties. Okay, the next one, this is the product property. Log base b of x times y is log base b of x plus log base b of y. The quotient property, and then the power property. Here's with this r comes down in the front. That's what that is right there. Okay, and then this last one is called the change of base property. Okay, so some calculators don't have log base b for any base. And so you can convert that log base. Let's say you had something like that, but it was more complicated. Then you could rewrite it like this. Okay, so number 10, we're basically going to use these properties. We're actually going to use these first properties to do number 10. Just these first properties, the inverse property. Okay, so let's go ahead and do that. Okay, so you have, it's log base 2, but 64 is also 2 raised to the 6th power. Okay, so 64 is 2 raised to the 6th power. Okay, so now here this 2 is the same as that 2, just like that b is the same as that b. So that means that this whole thing, it just becomes 6. Okay, likewise over here, you have log base 2. This is 1 over 64. So it's 1 over 2 to the 6th, or 2 to the negative 6. 2 to the negative 6 is the same as 1 over 2 to the 6, which is 1 over 64. Okay, so that one's going to be negative 6. This last one is a little bit tricky. But again, the key is you want to rewrite this as log base 32. Your base is 32. So the base is like pretty much fixed. You have to just go with what our base is. And then 2 is 32 raised to what power? Well, we know that if you raise 2 to the 5th power, we get 32, right? So if you take the 5th root of both sides, then you get that. So this is to the 1/5. Okay, and so then the answer is 1/5. Okay, so good. That's using the inverse properties. So let's go on to the next one. And here we're going to use these properties here, and we're going to rewrite this expression as a single logarithm. So when you do something like this, the thing you typically do first is this one right here, is to shift all the powers upwards. Okay, so this 1/7 you want to take that up here. And ln is the natural logarithm, so it works. All these properties hold for it as well. So when you pull that up there, it's 7 divided by 7, which is just going to be, we're just going to give you that log of x plus 2. Okay, now this one is a little bit tricky. Go ahead and distribute the 1/2 into both of these. Now we pull it up. And then this 1/2 comes up here, and it just cancels with that. So we have x squared plus 3x plus 2, like that. Okay, now we apply these two properties here, the quotient and the product, but just in the reverse order. So here we basically have this right-hand side. And so that's going to be x plus 2. X to the 1/2 is the same as just saying the square root of x. And then this is minus here, minus there. So this one goes in the denominator, like that. So maybe I shouldn't do too many steps at once. Let me backtrack a little bit and just write that as x to the 1/2. Okay, now it turns out that we can simplify this a little bit. I'll change it to a square root of x now. This factors into x, x plus 2 and x plus 1, and then the x plus 2 is reduced. And that's what you end up with. Okay, log of the square root of x over x plus 1. Any questions on that? Any problem with this? Okay, let's go on to number 12. And here we're solving some equations here. So first of all, that one. Okay, so now if it's an exponential equation, then what you want to do is take logarithms. Okay, so I'm going to take the log base 5 of both sides of the equation. Like that. And then I'm going to use this inverse property right here. And all that reduces down to just x minus 1. And then I just add 1 to both sides. And I get that. Wait, that's a 6 right there. I'm sorry. So 6 plus log base 5 of 4. Now, if you want to get an exact value and you don't have a calculator that can handle log base 5, then you just apply this change of base formula. So that would be the natural log of 4 over the natural log of 5. So 4 coming from here, 5 coming from there, just like this formula suggests. Okay, part B. I want to solve this. Now, to solve this one, what you want to do is you want to combine all of your logarithms together into one logarithm. So we'll use this property here. Like that. That's the first step. And the next thing that we want to do is what I call exponentiate. So the inverse of the natural log is the e, okay? So I'm going to start with e equals e, but then I'm going to put this in the power over here. And I'll put this in the power over here. Okay, now what happens is the e to the ln, this is from this property here. Those cancel or reduce down to just x times x minus 1. And of course, e to the 1 is just e. I'm going to distribute that in. So I get this. Okay, now I'm going to identify that this coefficient is 1, and this coefficient is -1, and this coefficient is negative e, and I'm going to apply the quadratic formula. Okay, so negative b, well, that's going to be 1 plus or minus the square root of b squared, which is 1, minus 4ac, so that's plus 4e. That's all over 2a, 2 times 1. Okay, so I have 1 plus the square root of 1 plus 4e all over 2. And I also have 1 minus the square root of 1 plus 4e all over 2. You have to be, when you do, okay, so when you do this step going from here to here, this could have additional solutions that this one doesn't have. So remember the domain so this bottom line is this answer here you have to throw out because this is negative. It's a negative number, and so you cannot put it into here. Okay, so the domain of ln of x is from 0 to infinity. So negative numbers are not part of the domain. Okay, so what happens? So what happened? Well, this number here is actually a solution to this. It actually works in this one because this is negative, and then this minus 1 is also negative. So those are both negative, so you can't even plug it into either of those places. But this one, you have two negatives multiplied by each other. So when you multiply them together here, they become a positive number. And so you can take the logarithm of this, although you can't take the logarithm of either of these. But it does work here. So this answer works here. This answer is positive already. It works here. It works here. So we're good. Okay, so so this should be the answer right here.